You start to. Wonderful. All right, so welcome to the October Virtual Astronomy Software Talks. We have two awesome talks today from both focusing on machine learning aspects applied to data analysis. We're going to start with Michelle Lochner, who has a joint position at University of Western Cape in South Africa and the South African Radio Astronomy Observatory. She's going to tell us about Astronomaly. Hopefully I'm saying that right. So anomaly detection. So I'm going to turn it over to her.
Thanks so much. Okay, so let me share my screen. See if I can just get rid of these. Okay, cool. Oops. There we go. All right. Well, thank you so much for the invitation to give this talk. It's really cool to connect with all of you guys. I love the idea of the seminar series. So yeah, I'm Michelle Lochner, as Mick said, and I'm going to be talking about how we can use machine learning to make new discoveries in enormous data sets. And this is work that I've done in collaboration with many people, and in particular with my students and postdocs in our affectionately named Computational Astrophysics and Machine Intelligence Lab. All right, so let me set the stage for this talk. So in 1967, one of the most important discoveries in astronomy was made. But I don't actually want to talk so much about the pulsar discovery itself, but rather about how this discovery was made. So the pulsar was discovered when a very bright graduate student named Jocelyn Bell Burnell carefully looked through all of her data, which at that time was just reams of pen on paper charts, and she noticed something very strange. And she made this incredible discovery that has really changed this entire field in astronomy. So the problem is that the question that I've been really trying to answer over the last few years is, how do we make these completely unexpected, groundbreaking discoveries when the SKA is going to deliver a catalog of 1 billion radio galaxies? And the Rubin Observatory, which is under construction in Chile, is going to have a catalog of 20 billion optical galaxies. And even worse, this telescope is so sensitive and has such a large field of view that it will discover 10 million things changing on the sky every single night. So one of those might be a Nobel Prize-winning discovery, but how on earth are we going to find it? There's just not enough grad students in the world to look through all of this data. So this is where machine learning, I think, can play a really critical role. So you may, I don't know how familiar everybody is with machine learning. I don't have time to do a very in-depth overview, but most machine learning applications that you hear about, like classification problems or regression, are a branch of machine learning called supervised learning. That's where you have some labeled data that maybe a human has said, this is a cat or this is a dog, and you have some amount of it, and you can train an algorithm to make new predictions based on unseen data, but it needs those labels. You can't do that when the thing that you're looking for has never been seen before, by definition. So you can't have any training data. So this is a branch of machine learning called unsupervised learning. And there are these anomaly detection algorithms that are designed basically to just take a look at a whole lot of data, try and identify what kind of normal looks like, and try and look for things that are far away from the norm. So some examples of machine learning algorithms that are used for anomaly detection include something like isolation forest, which is based on the very famous random forest classification algorithm, where in this case, the algorithm basically tries to make a series of decisions in order to isolate each point. And if it has to make lots of decisions, lots of cuts, that point is probably buried amongst a lot of its neighbors. And if it only has to make a couple of cuts, it's probably somewhere on the edge and therefore maybe anomalous. Another competing algorithm is called local outlier factor, which essentially just looks for points in low density regions. But when I started working on this years ago with my collaborator, Bruce Bassett, we realized really quickly that the anomaly detection step isn't really the hard part, and anomaly detection alone isn't enough. And that's because if you've got 10 million or a billion sources in your data set, you're going to find plenty of anomalies, but most of them are not going to be interesting. You'll have things like artifacts, which are obviously, well, to me, not interesting at all. But the thing is, the really curious thing about this is what's interesting is actually subjective. So I just said, I don't care about artifacts, but if you're in charge of the data quality pipeline for a telescope, you might want to know which artifacts your pipeline are missing. You might not care about the real sources. And even amongst things that are perhaps interesting, different scientists will be interested in different things. So there's a subjectiveness to this question of what makes an anomaly scientifically interesting. And this is where active learning plays an absolutely critical role. And I'm happy to go on record saying that we can't really successfully I don't think we could really do scientific discovery without some amount of human in the loop learning, at least not with the AI tools we have at the moment. So that means we combine the raw processing power of machine learning with the knowledge, intuition, and experience of a human user to try and get the best of both worlds. And the goal with active learning is always to try to be incredibly efficient with the human labeling. So you need human feedback, but you want to use as little as possible. So we don't want to waste people's time and have them looking through lots of random, boring sources. When you put all of these pieces together, you get Astronomaly. And I love the name, and it's good to Google. Nothing else in the world is called Astronomaly, but nobody knows how to say it or type it. But it is a general purpose anomaly detection framework for astronomical data. It's obviously publicly available. I would absolutely love for you to download it, play with it with your own data. Please reach out to me when you get stuck. But what Astronomaly is this pipeline, this combination between a Python backend and JavaScript frontend. It's designed to work with pretty much any kind of astronomical data. I say pretty much, it's not everything, but it can work with images in any wavelength. It can work with time series data, it can work with spectra. And the reason that it can work with all those different types of data is because it does this very important step called feature extraction, which I'll go into in a second. But this is the really most difficult part of any machine learning, or at least traditional machine learning pipeline, where you have to take a complicated piece of data like an image, which could have 100,000 pixels in it, and you have to simplify it down into a smaller set of meaningful numbers that a machine learning algorithm can use to solve whatever problem you are wanting to solve. After you've got your features, the rest is pretty straightforward. You can run one of those anomaly detection algorithms that I pointed out, and you can use this JavaScript front end, which looks like this, to actually interact with Astronomaly. And what you can do is you can give your images or time series or whatever a score out of 5 based on how interesting it is to you. And that will improve the machine learning algorithm so that it focuses on the more interesting anomalies. And it basically just downweights anything that it's pretty sure you're not going to be interested in because it's an artifact or whatever. So this is just a GIF of what it actually looks like to work with this interface. So you can see that I'm going through some images of optical galaxies, which come from the Galaxy Zoo dataset. And I've already ordered the data. So Astronomaly at no point tells you this is or isn't an anomaly. It just sorts your whole dataset from most to least anomalous by whatever it thinks is anomalous. So you can go as deep as you like, basically until you get bored. You're looking for things that are interesting. And what you're seeing is, as I'm clicking through this data set, I'm also giving it these scores out of 5 based on how interesting I think it is for me. And then I can run the active learning algorithm and improve it, basically, like I said, downweight the things that's not interesting. And if you go through the data sets, if you go through it from most to least anomalous, this is with the set of simulations, what will happen is initially it thinks, oh, you must be interested in the blue ones. And then I say, no, not really. They're okay, but they're not that interesting. I really like the green ones. And after a while, it'll start showing me more of the green ones than the blue ones. So it's basically a recommendation engine for astronomical anomalies. So a little bit like when you watch YouTube or Netflix, it tries to learn the things that you like based on what you've already watched. So Astronomaly kind of works in the same way, where it tries to prioritize stuff that's either completely new, you've never seen it before, so it has no training data, or is kind of like stuff that you've said is interesting. So this is kind of a flow chart of basically how it works. I never showed this slide, but I thought for this audience I could put it in. It's what you have to do if you're interested in using it. I didn't go with a purely GUI interface. You do have to do a bit of Python because I wanted to allow you complete flexibility in how you want to use it. So you can use it as a library, or you can use the interface. You can use it as you like. If you've got some huge complicated feature extraction process that you need to run externally on a supercomputer, you can run it and then just import your features however you want into the script that you write. So basically you write a little script which puts the pieces of Astronomaly together, reading in the data, reading in the features, or doing feature extraction, running an anomaly detection algorithm, etc. And then you give it the script to the server, and then it'll boot up this JavaScript interface that you could work with. And then you can iteratively score these anomalies and sort your data from most to least interesting. Okay, so that's kind of the heart of how Astronomaly works, but I wanted to talk about what we're doing with it in more recent years. Because I mean, Astronomaly by now is like 4 years old, so we've been adding quite a lot more to it. The biggest problem that I've been worried about and focusing on is that step of that feature extraction. It's really difficult to extract meaningful features, especially from images. The original paper, I had come up with a very simple set of morphological features that would basically just detect if things were kind of different from a disk. And it works okay. I mean, you'll find mergers and things like that, but it's quite difficult to find more similar things. It's not a really great feature extractor, but you know what the best feature extractors that we have is deep learning. And most people don't think of it this way. When they think of these deep learning algorithms, and I mean, really deep learning is the reason we talk about machine learning these days at all. It's incredibly powerful. But what people don't realize when they look at something like this, which is a ResNet architecture classifier, it's a convolutional neural network. It looks very complicated. There's all these layers. Your image goes in here and it does all these computations, and then out comes something, classification. Yes, this is a house or a cat. But what most people don't realize is that 99% of it is the feature extractor. That's what it's actually training to do. It's training to figure out how to simplify images down to meaningful features so that my last little layer can actually do the classification. So what we wanted to do was leverage the power of deep learning as a feature extractor for downstream anomaly detection. But this is kind of hard because, remember I said at the beginning, we don't have any training data, but these deep learning algorithms are supervised algorithms. They need to be trained. So what can we do? Well, the first thing that we did is used a CNN trained to solve a different problem and used that as a feature extractor for running it for anomaly detection. And that works extremely well. So this was work led by Mike Walmsley, who's now a Dunlap Fellow in Canada. And I don't necessarily have to go into it, but you can just notice that the blue line is much higher than the green line. And so that was the original work, and this is now using the deep features on the same data set. So this was a classifier trained to solve the complicated galaxy zoo classification problem. And we then took it, ran it on some new optical data, and we were able to do anomaly detection with Astronomaly very successfully. But there's something to keep in mind, and I'm going to come back to this. This is something called a UMAP plot, which you may or may not be familiar with, where we've taken the images, which are very complicated high-dimensional things, run a feature extractor. So now we've got something simpler. It's about 50 features. And then we run it through a UMAP plot to visualize it in two-dimensional space. So each point here actually represents an entire galaxy. And what you want from a good feature extractor is for similar galaxies to be in the same area of this plot. And the red and black points are the things that we're interested in. So these are considered anomalies in this data set. But what you should notice is that they don't actually appear very anomalous. So they're stuck kind of in the middle of the feature space instead of out on the outside. And this is a very interesting attribute of these deep features, which is something I've been working a lot on recently, and I'll get back to in a second. But nonetheless, it is an excellent feature extractor, and I'm very keen. I like to show that things work, but then I want to actually run it in the real world, run it out in the wild. So my PhD student, who's looking for a postdoc, by the way, just putting that out there, my very, very excellent PhD student, Roland Etzebeth, ran Astronomaly using that pre-trained feature extractor on nearly 4 million galaxies in the Decals dataset. And these are our top 18 most interesting galaxies. So we were able to show that it was extremely effective in real, large, unexplored data sets. I mean, nothing's been written about most of these. So they really are new discoveries. So, okay, remember I said that there's that complicated thing about how the interesting things are buried deep down inside. We're going to get back to that. And on the way, what we also realized is that we wanted to apply the same technique to new data. So stuff that's quite different from the things that the CNN was originally trained on. Like we wanted to apply it to radio data from Meerkat, which is a radio telescope here in South Africa. And for that, we have no training data. So we have no ability to pre-train an algorithm. So what we did instead is we turned to self-supervised learning. Self-supervised learning is absolutely the rage right now in machine learning for good reason. It's incredibly powerful. It's enabled things like ChatGPT. And I think it's really enabled anomaly detection in the image space. So what you do with self-supervised learning is you're skipping the step of solving some intermediate problem like classification, and you're just going straight to training an algorithm to be a good feature extractor. And the way that you can do this, there are a few different approaches. The one that we're using is an algorithm called Bootstrap Your Own Latent, where the idea is quite simple. If I take an image of a galaxy and I rotate it, or I zoom in, or I otherwise change it in a small way, I would expect to get pretty much the same features out. So these algorithms work by using these two different neural networks that work in tandem to basically aim to create a set of features such that that is true. That's the same image that's been augmented in a small way gives you the same features. And so we did this on, again, on the Galaxy Zoo dataset from scratch. It's about 200,000 images of galaxies, trained BYOL. And the cool thing is that we're able to apply an unsupervised clustering algorithm, which could automatically group together very similar looking galaxies. So you don't actually have to, in theory, you don't actually have to run a classifier. You don't actually need any labeled data. You can do all of this in an unsupervised manner. Just look at the clusters and say, oh, well, these are mostly spirals, these are mostly ellipticals. It won't be perfect, but it'll be a good starting point for building training sets for downstream classifiers. And the greatest thing is that we were able to use exactly the same algorithm without any changes to radio data. So I thought I had a slide on this, but I'm going to get back to this much later about this thing I've been teasing about dealing with these anomalies being buried in the deep features. All right, before I get to that, I just want to flash this up. I don't have time, ironically, to talk about time series, but we do have a couple of papers on running astronomaly or anomaly detection algorithms on radio transients and also optical transients. In particular, this paper, this very recent paper on optical transients, basically doing the same thing, using an RNN, in that case, trained to classify optical time series, and using that as the feature extractor to then do anomaly detection. And we're also, of course, looking at real-time anomaly detection, because just finding an interesting transient that happened 3 months ago doesn't help you very much. You need to be able to follow it up in real time. Okay, so finally, I'm going back to Meerkat and talking about those buried interesting anomalies. So I've been running these exactly the same approach, so self-supervised learning to extract features plus astronomaly to find the anomalous sources with Meerkat data. So this is with the Meerkat Galaxy Cluster Legacy Survey. And this is a screenshot of me again going through the MGCLS dataset. These are just randomly selected sources. So it's mostly kind of blobs, point sources, things like that. So most radio galaxies kind of look a bit like this. I've already done the selection to get only the extended galaxies. So they're not particularly interesting. But if you run Astronomaly and you order them by interesting sources, well, you really do get quite a lot of interesting things. The combination of Meerkat's incredible capabilities and Astronomaly has yielded quite a large sample of discoveries. So here's an example of them. If you're not used to seeing radio galaxies, I can guarantee that these are very weird, particularly things like this or things like this. We're excited about this one. So it's really very effective. But what we did have to do is really develop a different way of even thinking about anomaly detection. Because with these deep features, the standard anomaly detection approach just doesn't actually work. Because the things that are interesting are nicely grouped together, but they're not necessarily pushed apart in the feature space. There's nothing driving the feature extractor to make sure that that happens. So what we have is an algorithm we've called Protege, which is effectively a direct active learning algorithm. So we don't try to do the first anomaly detection step. We show a sample of sources and we have a relatively intelligent way of giving an initial sample. You label it as, yes, that's super cool. No, that's pretty boring. And very, very quickly, the algorithm learns to recommend things kind of similar to what you find interesting. And
Michelle,
yes.
You have about 2 minutes.
Perfect. That's perfect. I'm about to conclude. And then it's able to ignore the stuff that you don't find interesting. And it does have a sense of uncertainty. So if there's regions of feature space which are, it hasn't explored yet, it's going to prioritize those. So it learns that all of the things that you're finding interesting tend to kind of be around here, but some of them can be buried and it can still find them. So it's not really anomaly detection anymore. It's more like interestingness detection, but we're still focusing in on things that are rare and interesting. Okay, and this paper is hopefully finishing touches. So in a couple of weeks, this will all be out, and the latest release of Astronomaly will come out as well. All right, and I have to end with, in that MGCLS data set, we did actually discover something really weird. I have a good friend, Larry Rudnick, and I showed him this rather strange looking thing that Astronomaly found. And I said, hey, Larry, you're the expert. What is this? He said, I have no idea. Let's write a paper on it. We called it Sauron. It stands for a steep and uneven ring of non-thermal radiation. And the jury is still out as to exactly what this is. So anytime someone says, what has machine learning ever done? It hasn't ever actually discovered anything. You can say, no, it discovered Sauron. And we've got quite a few more discoveries on the way. Okay, this is like the philosophical conclusions, but I don't have a lot of any time really to talk about it, but I will in 30 seconds summarize it. So you found some anomalies. What do you do with them? Why do we care? Well, anomalies can be probes of the universe, like for instance strong lenses, fast radio bursts. They can pressure our models. You might find something that you can't explain, or more weird things than you were expecting. They're often probes of extreme physical environments, which is what we think Sauron is. But it's making me think a little bit about how do we prioritize follow-up? This is very high-risk science. It's hard to say to attack, hey, can I, go on a fishing expedition for this weird thing I found? So really the whole field of anomaly detection, which is growing rapidly, needs to think a little bit about these questions. And I'm going to stop there. Sorry for going a minute over time. Thank you.
That was a fantastic talk, Michelle. Thank you. Very nice to see how this is applied. Just a quick logistics. Sam, were you or I going to do questions? I can't remember.
I can field them, yeah.
Okay, why don't you do questions?
Okay. So does anybody have one or maybe one quick question for Michelle before we move on? We'll have time for open discussion later, but
there's one in the chat.
Yeah, I had one long question.
Okay. Let's see. Okay, so Mike says machine learning is progressing very rapidly. How does an astro student keep up with developments that might be applicable to their research?
When I figure that one out, I'll let you know. It's very difficult. It is a field that progresses unbelievably fast, and you can get incredibly overwhelmed trying to keep up with all the latest, greatest things that are coming out of the field. I would say, sorry, my cat's complaining at me, asking me to feed him. I would say that fortunately, I don't think we necessarily need to be on the absolute cutting edge all the time. I mean, we've been applying techniques that are 2-3 years old now, and they work spectacularly well. So if this is something that can solve your problem, I would say it's probably better to look at more established techniques that have kind of proven themselves, rather than always wanting to go for the latest, greatest thing. That being said, of course, you do want to be abreast of things and, you know, notice when gigantic things like ChatGPT and other transformers and LLMs are happening. So I think it's the same as keeping track of what's going on in research and astronomy. I mean, I use the archive. There's a great tool called Benty Fields. So I plug into the Astro archive and also to the machine learning archive, and I've trained it. It uses machine learning algorithm. I've trained it on the kinds of things that I'm interested in. So it's going to prioritize anomaly detection related research, self-supervised learning, etc. So that can really help. And of course, keeping abreast of the big machine learning conferences like NeurIPS, ICML is pretty much the standard way. But I would say that you are definitely not going to be able to keep track of everything that's happening, and that's okay. don't necessarily panic about that, but do keep an eye on techniques that come up again and again and have kind of proven themselves, which could be potentially useful for your research.
Okay, great, thank you.
Awesome. All right, we're going to move on now. Can't find this piece of scratch paper I wrote my notes on. Give me a second. Here we go. All right, and we're going to move on, and we're going to hear from Tomáš Plšek about CADET, machine learning for detecting cavities in noisy Chandra images. And Tomáš is coming up to us from Czech Republic. I wrote Masaryk University. I'm not saying that correctly. So
yeah, that's correct. Yeah.
Oh, it is. Wow. All right. So let's give our attention to Tomáš.
Okay, thank you so much. So yeah, first of all, I wanted to thank the organizers of Virtual Astronomy Software Talks for the invitation to talk about my pipeline. So hi, my name is Tomáš Plšek. I'm a PhD student at the Masaryk University in Brno in Czech Republic, and I want to talk about my machine learning pipeline for detecting X-ray cavities, which is called Cavity Detection Tool, or CADET for short. So before I introduce the pipeline itself, I just wanted to say like a couple of words about the physics behind, or what are we actually studying, because the utilization of this pipeline is like very narrow. It's not a general purpose tool. It's just like for studying AGN feedback, and not only one type of AGN feedback, because you're probably familiar with the classical like quasar or wind mode feedback, which is characterized by like optically thick disk that is relatively efficient, can lose most of its energy by electromagnetic radiation, and then we can observe it as a blazar or cipher type AGN or something like this. But what we're actually studying is the other type of feedback, the so-called radiomechanical feedback mode, for which it's characteristic that the accretion is in form of a optically thin torus. So it means that it's relatively inefficient. And that means that it cannot lose all of its energy via radiation. So instead, it actually loses energy by launching relativistic particles or jets of relativistic particles. And those are then observed as the so-called radio galaxies. How do we get to X-ray cavities? So when these jets are launched, they actually can inflate something called radio lobes. And when these jets and lobes interact with the hot X-ray emitting gas that is surrounding giant elliptical galaxies and galaxy clusters, it can actually inflate bubbles, and we call them cavities. And because it's the X-ray emitting gas, we call them X-ray cavities. So yeah, here you can see a nice visualization of that. So we've got a galaxy cluster, MS0735. So here is the optical image of the cluster with the brightest cluster galaxy in the center. And there's an AGN in the center of this galaxy, which is basically launching huge, enormous jets that can be seen here in the red color. And as these jets basically interact with the hot X-ray emitting gas, at the same position as these jets, we can see some depressions, like surface brightness depressions in the X-ray band. And those are basically completely spatially aligned with the radio emission. These cavities, they come in various shapes and sizes, but most commonly we approximate them by just ellipsoid or ellipses. And we can even have multiple generations of X-ray cavities, and they basically correspond to like individual subsequent discrete outbursts, most probably, as we believe. And not only that, there is also a phenomenon called ghost cavities, because usually we can see the radio counterpart, but only for the, let's say, innermost cavity generation. But when we look at outer generations of cavities, we usually see no radio counterpart, and that's why we call these like ghost cavities. And because they also like they are the only remnants left over by some previous AGN activity, and the only way how to study AGN activity in the past. And how can we actually study that? So yeah, let's imagine we've got a nice picture of a giant elliptical galaxy with really nice X-ray cavities. So we can just draw ellipses like this. From these ellipses, we estimate the approximate volume of those cavities. And then we can just take the pressure profile, which we can also estimate from the X-ray data. We can combine these two to estimate like energy or total enthalpy of those cavities. And if we put some time scale on that, then we assume that, let's say, they were inflated approximately at the speed of sound, but of course at the speed of sound at this medium, which is at approximately this big, we can even estimate what is the mechanical power of the jet that actually inflated those X-ray cavities. And this is already a pretty interesting quantity that we care about. And this way we can basically study those jet powers on very broad scale, because we can see cavities in like giant elliptical galaxies or galaxy groups, where the cavities are of the order of like the sizes of cavities are of the order of kiloparsecs, and the corresponding mechanical jet power is of the order of 10 to the 42 ergs per second. But we can also see X-ray cavities in, for example, brightest cluster galaxies like the Perseus in the center of the Perseus cluster, or in the center of M87, where the cavities are of one order of magnitude bigger. The jet powers are approximately 2 orders bigger. And then we can also actually observe some X-ray cavities even on the scale of the largest gravitationally bound objects, which is galaxy clusters, where the cavities can be actually as big as of the order of hundreds of kiloparsecs, and the corresponding mechanical jet power is actually comparable to a powerful quasar. Okay, so that's all nice, but of course, like there's always some problems, and the main problem is the data quality, because yeah, this is a really nice picture of a giant elliptical galaxy, and probably even like a small child would be able to tell that there are some bubbles over here, and even like draw ellipses to estimate their sizes. But actually, not all galaxies look like this one, or observations of galaxies look like this one. The usual observations look something like this. So yeah, you can see that probably somewhere here and here there are some cavities, but how do we draw the ellipses? Do we draw them like this, or do we draw them like this? It would probably differ scientist from scientist, and even like me myself, if I would do it in the afternoon or in the morning, whether I slept well or something. All of these would affect basically the estimated volume of those cavities. And there are even worse systems, for example, like this one, where we don't even know whether there are cavities in the system or not, just from the first look. And there are actually. But this whole thing looks like a really nice problem for a machine learning algorithm, for some image segmentation algorithm. But as Michel already said or outlined, those neural networks are usually supervised, which means that we need some training data in order to train them. So yeah, now I want to describe how did we actually create a training or gather a training sample. We could always use a real data, and the advantage of the real data is that they are realistic because it's real data, but the presence of cavities over there is always unclear. Even when there is a really nice image like this, we can never be 100% sure whether those are cavities or whether those are other features or something like this. And even if we were, we would still have to like estimate manually sizes of those cavities and basically draw those ellipse masks by ourselves, by hand. And a big disadvantage is also that basically only have like of the order of hundreds, maybe less than 200 images with known X-ray cavities. On the other hand, we could always simulate data, but the big disadvantage of simulated data is that we, of course, have to use some simplifications. We have to assume simplified models for galaxies, for cavities, simplified shapes. Everything is going to be azimuthally average or symmetric and so on. But if we simulate the data ourselves, we can actually directly control the presence of cavities. We can just turn it off on and on, whether we want to input cavities or not. We can well define the cavity extent. We just produce the cavities ourselves, so we know exactly where they are. And this way we can basically simulate an unlimited amount of images. So we have actually decided to go the other way and to simulate our
Am I the only one who's lost him?
every single, and also the rotations of those cavities can differ and so on, and the radii can differ. So we basically have something like 5 parameters that are describing the primary cavity, and then we've got another 5 parameters that are describing the secondary cavity with respect to the primary one. And yeah, these are the distributions of those parameters again. So we've got parameters like the distance from the center of the galaxy cluster or the galaxy, the radius of the cavity, the ellipticity of the cavity, rotational angle with respect to the rotational angle and rotational angle with respect to the direction towards the center of the galaxy. And you can see that in some cases there are actually some correlations, for example, between the radius and the distance. And there's like 3 reasons for that. We usually don't see cavities that are bigger than what they are separated by the galaxy from. So this is this part of the parameter space. Then they usually also grow up when they are getting into areas with smaller and smaller pressure. So they actually grow up as they get further and further away. That's this part of the parameter space. And there is also probably some selection bias because we don't see so small cavities so far from the center. So yeah, these are the primary parameters. Then we also did the same thing for secondary parameters, like for example, what is the fraction of the radius of the secondary cavity with respect to the primary one, and so on. Okay. And based on this, we've actually created parameters for our simulated training images. And we took those distributions and we sampled from those distributions using a Gaussian kernel density estimation. And we actually also took into account the correlation between individual parameters. And so we've got something like, in this case, we've got something like 10 parameters. So it was a 10-dimensional parameter space in which we estimated those correlations and so on. It was basically automatic using this Gaussian kernel density estimation. And why did we actually do this? Why didn't we just estimate the ranges of those parameters and then just populate these parameter ranges like uniformly, for example, or log uniformly or under some assumption? Is that we basically had to care about these parameters and their correlations because, for example, here you can see a nice plot like the dependence or basically the distribution for core radii and amplitudes. And you can imagine that for example, for the beta model, these 2 parameters are quite crucial and they will affect the resulting quality of the image and how many counts we will basically detect. Of course, there's also the exposure and so on. But you can see that, for example, if we would populate this part of the parameter space, we would be basically creating images that have very few counts and they are not suitable for training. And on the other side over here, we would be generating a lot of images that have so many counts and they are also not very useful for training because we want to use it for data that actually look like this they have the order of like tens of or hundreds of thousands of counts, not like millions or billion counts. And then, of course, some parameters were generated like completely randomly. For example, the positional angle of the primary cavity or the positional angle of the beta model and so on. So yeah, this way we basically generated 128 times 128 images and corresponding masks. So here you can see, so this is the image of a galaxy with some X-ray cavities inserted. And this is the corresponding cavity mask. This is the label that is basically used for training. And then we also further process those images. We basically convolve them with Chandra PSF because the pipeline is optimized for images of Chandra from the Chandra X-ray telescope. And then we also applied Poisson noise to make the images look like realistic images. And we also added some other features that are typically observed in around X-ray cavities or in giant elliptical galaxies and clusters. One of them is cavity rims. Sometimes the inflation of cavities is just slightly supersonic, something like 1.2 Mach number. And then we can basically see weak shocks at the edges of X-ray cavities. So we also try to simulate that, of course, using some empirical parametric model. And then we also try to very simply simulate sloshing, which basically when we have a merger, this is the pattern that we basically get.
Thomas, you have about 5 minutes.
Okay, yeah, thank you. I'm gonna speed up, rapidly. Okay. And this way we basically generated a huge set of images, like of the order of million of images. And we did that actually on the fly using GPU because this whole process was implemented using JAX library. This is what the training images look like. Sorry about that. So these are the training images with X-ray cavities. We also generated images without any X-ray cavities. Now I'm gonna very briefly describe the architecture. So we use a convolutional neural network with inception modules. We basically have like several parallel convolutional filters that can probe, or as we believe, they should be able to probe like features on individual size scales. And we've got, sorry about that, we've got like 5 inception like blocks stacked behind each other. There's a fixed input size, 128 times 128 image. And on the output, there is an image of the same size with values ranging from 0 to 1. So at the end of the day, this is basically like a pixel-wise binary classification into not a cavity and one, yes, a cavity, most probably. And then this whole thing is decomposed using the DP-scan clustering algorithm into individual cavities. This whole step is just for automation, because this is instant segmentation, this is semantic segmentation. So we had to basically cut it into individual X-ray cavities. I don't think this is really necessary. So here I'm basically describing how we trained the network. We also tested not all the images contained X-ray cavities. Some of the training runs, only 50% of the images contained X-ray cavities, and so on. And the whole training took something like 8 hours. And we trained it for 32 epochs. And then after this was just the CNN. This is how we trained the convolutional neural network. And this we combined then with the DB-scan clustering algorithm. But this whole thing was then also made into a pipeline where we wanted to make the prediction more robust. So we are not only inputting like one single image, but we're actually doing something like 25 central pixel shiftings plus 4 rotations. So at the end of the day, we've got something like 100. The final prediction is composed from something like 100 of partial predictions. The predictions are thresholded because to get rid of some low significance features. And then we, of course, only take some predictions as valid if they can be found on like several multiple subsequent size scales. Usually it's a multiples of 128 images just binned into 128 pixels, sorry. And then, I wanted to describe how we are actually getting from the 2D pixel-wise prediction into 3D cavities. And then I wanted to describe how we actually tested the pipeline. So we tested it on simulated data. So it was quite successful because it was trained on simulated data. So here you can see some plots. This is like the predicted volume versus the true volume. And you can see that it pretty nicely follows this unity line. And then, for example, it also differs how many counts does the original image have. So you can see that if the image has something more than 100,000 counts, the relative error is within this range of around 20% in volume, which is like 6% in radius. But when we're getting into the area where there are less than, for example, 10,000 counts, the relative error is much bigger, and also, for example, the true positive rate is decreasing and the false positive rate is increasing. We tested it also on real data. So here you can see some predictions of real X-ray cavities. It was actually quite successful, and we even tried to put some numbers on that. So we actually detected 94 out of 98 known X-ray cavities with a volume difference of the order of like 20 up to 70%. in volume. Okay. Yeah, we also managed to detect X-ray cavities in some pretty distant sources, like for example this galaxy cluster, which is at the redshift of 0.4. And then we also tested the pipeline on images that for which we didn't know X-ray cavity that there were X-ray cavities in these systems. Sorry. And we actually managed to detect 7 new pairs of X-ray cavities and something like 8 cavity candidates. And how you can actually use CADET? As I said, it's basically a single-purpose tool. It's only for detecting X-ray cavities on X-ray images, ideally on Chandra images. But you can use the raw model, which you can load using Keras. I also made it into a nice online tool that is hosted on Hugging Face. You can check it out if you're interested. Then I made it into a Python package called PyCadet. It's on the GitHub page, I've got a nice tutorial on that. And then the very last thing I wanted to show, I also managed to make it into a DS9 plugin, but currently this is still under development. I still need to figure out how to fix it, but this is basically what it works like. Sorry about that. I open the image in DS9, I select box region like this. Yeah, I select the box region like this, then I can click analysis. Cadet, I can set some parameters. I click OK. Now it's gonna take a while to crunch it and to process it. I don't have a dedicated GPU, that's why it takes so long. And there you go. This is the output. So this is the pixel-wise prediction. This is the output of the DB scan after decomposing. Here are contours overlaid over the original image, and these are parameters of those cavities. Okay, sorry for being too long, and yeah, thank you for your attention. And that's it. I'll probably leave you with this slide, what I'm planning to do next.
Well, that was very nice.
Okay, sorry for not being on time and for it.
It's okay. I mean, we're all fascinated by both of these talks today. I'll leave things in Sam's hand to finish off questions for the remainder of the hour.
Yeah, sure. So I did have some questions, but if anyone else has questions, feel free to put them in the chat or speak up. First, Mike has one. He wants to ask the same question to you, Tomáš, that he asked to Michelle, which was, how do you keep up and learn about machine learning that can be applied to your research?
You don't. You don't. I think it's super hard even for computer science students or even for people doing machine learning to keep up with all the new stuff. I think it's for an astronomy student, I think it's impossible. You can always just use tools that somebody else already developed, and you just have to learn how to use those tools. And even in my case, I didn't develop. I basically took a pipeline that I basically took a project that was already existent, and then I just continued. And the most part of my work, or what I did in this whole project, was that I created those training data, and then I just slightly played with the pipeline or with a model that somebody has already created. So yeah, I think it's really hard, and yeah.
Okay. That's perfect. Thank you. I think, Michelle, did you have your hand raised?
I did. I wasn't actually sure if it went up. Thanks for that, Tomáš. That was a really interesting talk. And I was going to say it in the chat, but it might be the first time I've seen someone train an algorithm on simulated data and it actually works on real data. I don't think I've ever seen that. So that's kind of amazing. Although I had the same question as Sam about what was the false positive rate, because you talked about the recall. But I also had a different question, which was that your use of JAX was really interesting for actually doing the simulation. So I haven't used JAX much. I wondered if you could talk a little bit about your experience of it. Was it really easy to get started and to do what you wanted to do, or has it got a bit of a learning curve?
Oh, in the case of JAX, I actually had the whole process of generating the data already implemented using NumPy. And JAX, it basically has this module for NumPy.
Okay.
So yeah, I would love to say that the only thing I did was change the import, but it wasn't that easy. I had to actually take care of the types. Certain functions work slightly differently than classical NumPy, but I didn't really use any sophisticated JAX function. The only thing I did that I basically like precompiled single functions at the end, so that it runs much faster.
Okay. That's cool. So it's kind of a bit like number then, I guess, in that you don't have to do too much, but there's a few rules that you kind of have to follow.
Yeah.
But it's
And
nice to
regarding
see it running on.
And I just wanted to say that I was also super surprised that it worked after trained on simulated data. So yeah, I've also seen some cases where people try to train on simulated data and didn't usually work. And I was surprised that it did in this case, and it did even work for real data very well. And now recently there's something I wanted to add, but I didn't have time. They even used it to detect cavities in simulations, like TNG simulations. So it's also like different type of data, but it still somehow works. And regarding the false positives, it's usually, for example, in a galaxy like this one, like yeah, maybe like this one. The usual case of false positives was right behind some bright features. So for example, these rims, bright rims around X-ray cavities. So what the model did tend to do was to basically detect false positives right behind the edge or something like this.
Okay, perfect. Yeah, thank you. That's what I was wondering about. I guess I will ask one more question. So you said you detected 94 of 98 real cavities, which is very impressive. But I'm just curious about the 4 that it didn't detect. Do you know what was there some special feature about those that the algorithm didn't pick up on, or why weren't those 4 caught, I guess?
To be honest, I don't know for 100%. I don't remember like individual cases because it's been a while when we did this. But I do remember, for example, one case that we knew based on radio data, and the cavity was not really visible in the X-rays, but we could see nice radio lobes, and we could see the bottom cavity co-aligned with the radio lobes. So we somehow thought that yes, there might be a cavity on the other side. And actually, like when we did the residual image and we focused on our eyes on that area, we could see the cavity, but it was very low signal to noise compared to the background. So the brightness drop was not significant, and that's why also CADET had problems with that.
I see. That makes sense.
I have a question. I'm wondering if the speakers are willing to share their slides. If you could send us your slide decks so we can attach them to the VAST website. This is particularly important for Thomas's talk because my internet connection, apparently, I'm in a hotel, so the internet connection died a couple of times and I don't know how much of the recording we got. So
yes, I can definitely do that. Yeah.
okay, great. If you could just email them. Great. Thanks so much.
Wonderful. And Michelle and Thomas, these were 2 excellent talks. So I really want to thank you, especially given the time zone difference, for being available and to present to us. We will upload things on YouTube so others in the community can benefit, but you're both doing very exciting work. So thank you for sharing.
Thank you.
Yeah,
Thanks so much for inviting us.
That was great. Thank you both. And if anyone has suggestions for talks that they would like us to try to feature, please let us know. Send an email to any of the organizers. Names are listed on
Or do it on our GitHub page. Yeah.
Or do it on our GitHub page. That's right. So if you can put that link up, can I put that link up?
Probably good. Gotta find the chat.
There.
Yeah.
How's that? Or there. Yes, that's good. Thank you.
Alrighty. I think it's the end time. So thank you again, everyone. Thank you for joining us. Good evening to those of you 8 hours ahead or however far ahead you are.
Thank you so much.
Thanks,
Thanks, everyone.
Thank
Bye-bye.
you all.
Yeah, thank you so much for inviting me. Yeah, bye-bye.
Thank you. Organizers, if you could hang back for a minute.
Yeah.
I just want to see if anybody happened to catch the video when.
Can you stop the recording?
Yes.